In today's lesson, we are going to begin learning about polar graphing. We are going to start by talking about how we graph in a polar coordinate system. Then we will take a look at how to do distance formula in a polar graphing system. And lastly, we'll take a look at some simple graphs as lines that go through the origin or the pole and a circle with our center at the pole. When we talk about polar graphing, instead of using the typical x, y that we are used to, all points are in the format of r, theta. The origin of our graph is at the center, and we now call this the pole. The positive x-axis is the polar axis, that would be right here, and r indicates how far this point is from the pole. The theta indicates the direction of the point in either radians or degrees. If we look at our graph right here, what we will see is that we have angles similar to what we're used to from our unit circle days. So this would be like our 30 degrees or pi sixths. This would be our 60 degrees or pi thirds. And then up here we have 90 degrees or pi halves. So if I were to take a look at the point that is located right here, this point is 1, 2, 3, 4, 5 rings out from the center. So if on this graph, if my scale was that one ring equals 1 unit, then I could say that this point right here in blue could be represented by 5, 30 degrees. I could also say that this point is 5 pi 6. So every point that we look at is going to be of the form r theta. Now when we are graphing, if we are given a point where the r value is negative, then what that means is we are going to go in the opposite direction. So for example, if I were to give you the point -5, 210, that point would actually have the same location as if I gave you the point 5, 30 degrees. Because what's going to happen is I'm going to locate an angle at 210 degrees, and then because this r value is negative, I'm actually going to go in the opposite direction. So for this reason, whenever I have a point that happens to have a negative r value, I can rewrite it with a positive r value by simply adding or subtracting 180 or pi. So let's write that down. Any negative r value can be rewritten as a point with a positive r value by changing theta by 180 degrees or pi radians. Alright, so if we go ahead for this next section, we want to find a different way to name each of these points. Let's start by actually graphing these points. I'm going to do E in red, I'm going to do F in blue, and I will do black in G. So for point E, since it has a negative angle, that means I'm going to go backwards, and this point is going to be located 3 rings out at -90 or 270 degrees. So an alternate way we could name this point is 3, 270. And again, all we did was change the angle to an angle that is coterminal with it. So point E will be located right here. When I go to do point F has a negative radius. So recall, we can rewrite any point with a negative radius by changing it to a positive radius and then adding or subtracting a pi, in this case because we're dealing with radians. So I'm going to add pi so that I can keep my angle positive. So adding 3/3 pi would give me 2, 5 pi thirds, which would be located right here. And then lastly, for point G, I have a negative radius and a negative angle. So you can choose to change either one of those. What I'm going to do is I'm going to change the radius to +5, and I'm going to do that by adding 180. So not only does that fix the negative radius, it also fixes the negative angle, which gives me the point 5, 120. 2, 3, 4, 5. And that would be right here. Our default scale for our graph is that each ring is equal to 1 unit. If you want to scale your graph otherwise, then you just specify on a key the same way we would do with regular graphing. Another thing that I want to mention is what would happen if I gave you a point with a radius of 0. Let's say, for example, we created point H, and we said that point H had a radius of 0 and 120 degrees. Well, any point with a radius of 0 is going to be at the pole. It doesn't matter what angle we have. If it is 0 circles away from the center, then that point is always going to be located at the pole at 0. Okay, let's go ahead and take a look at how the distance formula would play out in a polar system. Now we have 2 points here, point P1 and point P2, and these are defined with having R1 theta 1 and R2 theta 2. If we just put these points anywhere on our graph, let's say we put point P1 right here, we'll call that P1, and let's say we put P2 over here somewhere. Now, if I'm trying to find the distance between these 2 points, I can't exactly do Pythagorean theorem like I would if I were on a rectangular coordinate plane. So instead what we're going to do is we're still going to make a triangle. However, this triangle, the 2 sides are going to be found by drawing in the segments that connect the pole to the points. Now when we try and figure out the lengths of these 2 thicker red lines, think about how polar graphing works. Points P1 and P2 are a distance of R1 and R2 from the center. So the length here is equal to R1, and the length over here is equal to R2. So if I want to find this distance between the 2 points, I can just go ahead and do law of cosines to find that length. Now in order to do law of cosines, we know R1 and R2 because those are the radiuses, or the radii of the 2 points. What we need to find is this angle in between. And in order to get that angle in between, what we're going to do is we will subtract the 2 angles. So to find the angle, we are going to do theta 2 minus theta 1. Now, one thing that I would suggest is I always rewrite my points with positive r's and positive thetas before doing these problems. You don't have to, but I just find it easier to visualize what the angle should look like. So what we're going to do is we're going to use law of cosines to find our distance, and we will say it'll equal r1 squared plus r2 squared minus 2 times r1 times r2 times that cosine of the angle that's in between them. And like I said, I always suggest that you rewrite your points so that r and theta are positive. Another thing that I suggest is while you're still learning especially is that you draw a quick sketch. Again, none of these things are required, but I find it helps people make less careless mistakes. Okay, for example 3, we have 2 points. Both of these points are written such that the r's and the thetas are positive. And what I mean when I say draw a quick sketch is that we would just draw a quick graph, and the point 4170 would be located about there, and the point 6105 would be about there. Again, these are just estimates. We're just eyeballing where 170 and 105 degrees would be located, and the point that has a larger radius is farther from the origin or the pole. Alright, so if I were to draw in my triangle, I know that this side has a length of 4, this side has a length of 6, and then this would be my distance that I'm trying to find. When I'm trying to figure out the angle in between, I just do 170 minus 105, and I get 65 degrees. So now, to solve for my distance, I can simply say the distance equals square root of 4 squared plus 6 squared minus 2 times 4 times 6 times cosine of 65 degrees. And we will get 5.362 units. All right, for the next example, I want you to practice rewriting these points so that they have positive r's and thetas, drawing a sketch, and then calculating your distance. Your correct answer will be 3.162. Pause the video and take a few minutes to try and figure this out. Okay, when figuring out example 4, the first thing that I did was I rewrote the points so that they had a positive r value. I did this by changing the r value to the positive and then adding or subtracting a multiple of 1 pi. So in this case, I added 8 eighths, giving me 9 pi eighths for the first point. And then for the second point, I added 5 fifths, which gives me 3 pi fifths. Then I drew a quick sketch, and while these angles are not ones that we know off our unit circle, we should know that 9 eighths is a little bit bigger than 1 pi, and that 3 fifths is a little bit bigger than pi halves. And that gives us a decent estimate as to what our graph should look like. Now we need to find that angle in between the two segments. And to find that, we just subtract the angles, and after making like denominators, we get 21 pi 40ths. All right, now it's time to go to law of cosines. For law of cosines, we simply say that that segment length is equal to 2.5 squared plus 1.75 squared minus double their product times cosine of the angle in between 21 pi 40ths. And then after we type this in the calculator, we get 3.162. All right, pause the video and take a minute to check in with your neighbor before we look at our last topic. All right, last thing that we're going to look at today are simple polar graphs. We will take a look at some much more complicated polar graphs tomorrow. However, for today, we're going to look at basic circles and lines. Now, the first one is a basic circle with a radius of the absolute value of r, and the center of the circle is at the pole. So if we look at these two examples here, I'll do the first one in blue. Radius of 4, we simply go out 4 rings, 1, 2, 3, 4, and then draw a circle on that ring. Hopefully yours looks nicer than mine. The one where we have r equaling -6, we'll draw this one in red. The radius is going to equal the absolute value of -6, so we just go out to 6 rings out and draw in another absolutely fantastic circle. All right, for the next one where we just have theta equals an angle, this is going to look like a line through the angle theta. So for example here, when I see theta equals 2 pi thirds, I'm going to locate the angle of 2 pi thirds, and then I just draw a line that goes through it. Remember, a line has an arrow on both sides, so make sure you do that. If my angle is negative, I will find that -45 degrees, and then just draw my line through it. So the line theta equals -45 also looks the same as the line theta equals 135. So again, we can add 180 to make that angle positive and see what it would look like here. All right, that's it for today. Thank you.